He found it while cleaning out his mother's house, a manila envelope with his own name on it in her handwriting, an X-ray from when he was 9, the year he fell out of a tree and broke his forearm. He held it up to the kitchen window, the way she used to hold it up to the hallway light back then, standing next to him and pointing at the crack running through the bone like she was reading him a story. 2 pale bones, a hairline break, healed into a faint, thickened seam, a hand that was unmistakably his, and yet nothing like the hand he was holding it with. He had a more recent scan on his phone, from a sports injury the year before, and he pulled it up next to the old film without really thinking about why. Same forearm, same person, and it struck him, standing there, that not one atom in that 30-year-old X-ray was still inside him. Not one. The calcium, the phosphate, the collagen scaffolding holding it all together, all of it had been replaced, torn down and rebuilt, more than once, somewhere along the 3 decades between the boy who fell out of a tree and the man holding 2 pictures of the same bone in his own kitchen. What he was looking at was not a record of change in the way a photograph shows you aging, the gradual softening of a face, the slow graying at the temples. It was something stranger, closer to discovering that a house you'd lived in your whole life had quietly had every brick replaced while you slept, one at a time, without the walls ever coming down or the address ever changing. The bone itself, the physical material, had been swapped out, piece by piece, while somehow remaining recognizably the same bone, doing the same job, in the same place. Your skeleton is doing this right now, inside you, as you read this sentence. It has never once, since the day you were born, stopped rebuilding itself. If you're enjoying this story so far, don't forget to hit the like button and subscribe. Drop a comment telling me where in the world you're watching from. I love hearing from you. Bone looks finished. It is white, hard, and still in every image you have ever seen of one, the classic cartoon skeleton hanging in a biology classroom, motionless and permanent. That stillness is an illusion created by the timescale humans are built to notice. Bone is, at every moment of your life, a construction site. 2 populations of cells run this project, and they work in permanent, deliberate opposition to each other. Osteoclasts are the demolition crew, large cells that attach to the surface of bone and dissolve it, releasing the calcium and phosphate locked inside, back into the bloodstream, and clearing space for what comes next. Osteoblasts are the construction crew, laying down new collagen scaffolding and mineralizing it with fresh calcium phosphate, rebuilding what the osteoclasts tore down, though rarely in the exact same spot at the exact same time. This paired process, resorption followed by formation, is called bone remodeling, and it runs continuously across your entire skeleton in millions of microscopic locations called basic multicellular units, each one a tiny, self-contained renovation project a fraction of a millimeter wide. The pace of this rebuilding is not uniform across your skeleton, and the honest picture is more textured than the popular claim that your entire skeleton replaces itself every 10 years. That figure is a reasonable average, but it hides real variation. Trabecular bone, the spongy, lattice-like tissue found inside vertebrae and near joint surfaces, has an enormous surface area relative to its volume and turns over quickly, with some estimates placing full trabecular turnover somewhere in the range of 3 to 4 years. Cortical bone, the dense outer shell that makes up most of your long bones, like the femur and tibia, turns over far more slowly, with parts of it persisting for a decade or more before being replaced. A 10-year average across your whole skeleton is a fair approximation, but the shaft of your thigh bone and a vertebra in your spine are, quite literally, running on different clocks. None of this is chaos. It is closer to a city that never stops repairing its own roads, section by section, without ever fully closing down, and the crews doing that work are responding to a signal, a very specific one, that tells them exactly where the next repair needs to happen. The remodeling cycle at any single location follows a fairly consistent internal sequence, regardless of where in the skeleton it happens. Osteoclasts arrive first, drawn to a specific site by signaling molecules released in response to mechanical microdamage or simple routine turnover. and spend roughly 2 to 3 weeks dissolving bone at that location, carving out a small resorption cavity. Osteoblasts then move in, a process that typically takes considerably longer, 3 to 4 months in many locations, laying down new collagen matrix and mineralizing it in careful layers until the cavity is filled back in, ideally to match the strength and geometry of the surrounding bone. The demolition phase is fast. The reconstruction phase is slow and deliberate, which is part of why an imbalance between the two, even a small one sustained over years, has an outsized cumulative effect on total bone mass. In 1892, a German surgeon named Julius Wolff described something orthopedic doctors had suspected for decades. Bone adapts its internal structure to the mechanical loads placed on it. Load a bone heavily and consistently, and it grows denser and stronger along the lines of that stress. Remove the load, and the bone thins. This became known as Wolff's Law, and for roughly a century it sat as an observed pattern with no known mechanism. Bones have no eyes, no nerves running through their mineralized core the way skin does. Nobody could explain how a bone actually detected that it was being used. In 1957, a Japanese orthopedic surgeon named Iwao Yasuda ran a simple, almost blunt experiment. He took a piece of dry bone, attached 2 wire electrodes to it, connected them to a voltmeter, and squeezed the bone in a press. The needle on the voltmeter moved. Squeezed bone, with no battery and no external power source, generated a measurable electrical voltage on its own. This is called the piezoelectric effect, from the Greek word for squeeze, a property shared by materials like quartz crystal, in which mechanical stress physically displaces electrons within the material's structure and produces a small but real electrical charge. Bone, it turned out, does the same thing, driven primarily by the collagen fibers within it, long twisted protein strands that generate a voltage gradient when bent or compressed. That voltage is the missing mechanism Wolff's Law never explained. When you walk, your leg bones flex under your body weight by an amount too small to feel, and that flexion stresses the collagen fibers inside the bone, generating a tiny electrical signal at the site of greatest mechanical stress. Osteoblasts and osteocytes, a third type of bone cell embedded deep within the mineralized matrix that appears to function as the network's primary sensor, respond to that localized electrical and mechanical signal by directing new bone formation specifically where the stress occurred. The demolition and construction crews are not working randomly. They are following a map drawn in real time by the mechanical forces moving through your skeleton every time you stand, walk, or lift something heavy. A genuinely elegant answer to a question that took orthopedic medicine 100 years to solve. This discovery moved out of the laboratory and into clinical practice more directly than most basic science findings ever do. Bone growth stimulators, small medical devices placed near fractures that have failed to heal on their own after the normal expected time frame, work by delivering a weak external electrical or electromagnetic signal directly to the injury site, effectively imitating the piezoelectric signal a healthy, loaded bone would generate on its own. The devices do not replace the biological remodeling process. They attempt to restart the specific electrical conversation between mechanical stress and cellular response that a stalled, non-union fracture has stopped participating in, giving osteoblasts a signal to respond to even in a bone segment that, because of its injury, is not currently bearing the load that would normally generate one. If mechanical loading is the instruction telling the construction crew where to work, the obvious next question is, what happens when that instruction stops arriving altogether? NASA found the answer by accident, and it alarmed them. Astronauts spending extended time in microgravity began returning to Earth with measurably weaker skeletons, and the rate of loss was startling. Studies of astronauts on long-duration missions have documented bone density losses in weight-bearing regions like the hip and spine of roughly 1 to 1.5% per month, a pace that dwarfs the roughly 1 to 2% per year lost by an elderly person with significant osteoporosis on Earth. In microgravity, bones experience essentially no mechanical loading. There is no weight pressing down through the skeleton, no piezoelectric signal generated by flexion, no instruction reaching the osteoblasts telling them where new bone is needed. The osteoclasts, meanwhile, continue their resorption work largely unaffected by the absence of gravity, and with construction paused while demolition continues, the skeleton loses ground. You do not need to leave Earth's gravity for a milder version of the same imbalance to occur. Extended bed rest, prolonged immobilization after an injury, and a simply sedentary lifestyle sustained for years all reduce the mechanical loading signal, reaching the skeleton, shifting the balance of the remodeling cycle toward net loss, even while gravity continues pulling on the body normally. This is part of the physiological reasoning behind weight-bearing exercise as a specific recommendation for bone health. Not exercise in general, but exercise that actually compresses and flexes bone under load, since that mechanical stress is the only reliable trigger for the piezoelectric signal the construction crew is listening for. Swimming, valuable as it is for cardiovascular health, provides comparatively little of this specific signal because water buoyancy removes much of the load bones would otherwise carry on land. Space agencies have spent decades developing countermeasures precisely because the bone loss problem threatens the feasibility of long-duration missions, and the countermeasures that actually work confirm the mechanism rather than working around it. Resistive exercise devices aboard the International Space Station, designed to let astronauts perform loaded squats and deadlift-style movements against mechanical resistance in the absence of gravity, have measurably reduced, though not entirely eliminated, the rate of bone loss compared to earlier missions that relied primarily on cardiovascular exercise, like treadmill running, secured with bungee harnesses. The countermeasure that works is the one that recreates genuine mechanical loading on the skeleton, not simply physical activity in a general sense, a finding that maps directly onto Yasuda's original piezoelectric discovery decades earlier. The bone is not asking to be tired out. It is asking to be squeezed. If you're hooked on this story, make sure to subscribe and turn on notifications so you never miss an upload. Your support means everything and helps me bring you more emotional stories like this one. Knowing that bone remodels does not by itself prove the atoms are different. It is possible, in principle, for cells to tear a structure down and rebuild it using largely the same raw material recycled on the spot. Establishing that the atoms are genuinely turning over, not just the architecture, required a separate and more direct line of evidence. Some of the clearest evidence comes from an unlikely source: nuclear weapons testing in the mid-20th century. Above-ground nuclear tests conducted before the 1963 Partial Test Ban Treaty released a sharp pulse of radioactive carbon-14 into the atmosphere, roughly doubling its natural background concentration within a few years. That carbon-14 entered the food chain through plants performing photosynthesis, then into the animals and humans who ate those plants, creating a detectable, dated spike embedded in the carbon of every biological molecule formed during and after that period. The atmospheric concentration of carbon-14 has been declining in a well-documented curve ever since, which means the carbon-14 concentration inside any particular cell or tissue functions as a kind of timestamp, revealing roughly when the carbon in that tissue was actually incorporated from the atmosphere. Researchers led by Kirsty Spalding and Jonas Frisane at the Karolinska Institute used exactly this bomb pulse signature to answer a genuinely difficult question directly. Which tissues in the adult human body are actually being rebuilt, atom by atom, and which are frozen in place from an earlier point in life? Their work, published in Cell in 2005 and extended in later studies, found real variation across tissue types. Fat cells turn over at a measurable, moderate rate. Certain populations of neurons in the adult brain, particularly in regions involved in memory formation, showed evidence of ongoing generation well into adulthood, a finding that overturned decades of assumption that the adult brain generated no new neurons at all. Skeletal tissue, examined using the same isotopic method, showed clear evidence of ongoing turnover consistent with the remodeling cycle bone biologists had already described, through more direct means. Cortical bone samples showing carbon-14 signatures reflecting material laid down years after the person's birth, rather than at it. The atoms making up your skeleton right now were, for the most part, not present in your body at any single earlier moment you could point to. They arrived from food, were built into bone matrix by osteoblasts at some point in the recent past, and will eventually be dissolved by osteoclasts and either recycled into new bone elsewhere or excreted entirely. The specific calcium ion sitting in a particular spot in your femur today has its own individual history, arriving from a meal weeks or months ago, and it will not remain in that exact location indefinitely. Your skeleton holds roughly 99% of your body's total calcium, functioning simultaneously as a structural framework and as the body's primary calcium reserve, a dual role that adds another layer to why the atoms inside it are never truly settled. Blood calcium levels have to stay within a narrow range for basic processes like muscle contraction and nerve signaling to function correctly, and when dietary calcium intake falls short of what the body needs on a given day, hormonal signals, principally parathyroid hormone, trigger osteoclasts to release stored calcium from bone directly into the bloodstream to cover the shortfall. This means the constant atomic turnover in your skeleton is not only a byproduct of mechanical remodeling, it is also, in part, your body actively using bone as a mineral bank account, making regular withdrawals and deposits that further guarantee the atoms present in any given bone today are not the same ones that were there a year ago. The remodeling story becomes more interesting, not less, once you learn it is not universal. Some structures in the human body are built once, early, and then never meaningfully replaced for the rest of your life, which makes them a useful contrast for understanding what makes bone different. Tooth enamel is the clearest example. Enamel is produced by specialized cells called ameloblasts during tooth development, and once a tooth erupts into the mouth, those cells die off and enamel receives no further cellular maintenance at all. It is, biologically, closer to a secreted mineral deposit than living tissue, incapable of self-repair the way bone is, which is precisely why a cavity in enamel does not heal on its own the way a bone fracture does. The enamel on your teeth right now is, atom for atom, largely the same enamel that formed when those teeth were developing, decades ago in the case of adult teeth, making it one of the few genuinely permanent structures in the human body. The lens of your eye follows a related pattern. Lens fiber cells are generated early and continue accumulating in layers throughout life, but the cells at the very center of the lens, formed earliest, are never replaced or removed, essentially trapped at the core for a lifetime, which is part of why lens proteins are unusually long-lived, and why age-related changes to the lens, including the gradual stiffening involved in presbyopia and the clouding involved in cataracts, reflect decades of accumulated molecular damage to material that was never refreshed. The Spaulding and Friesen research found a similarly striking result for the neurons of the cerebellum, and more strikingly, for cardiac muscle cells, which do turn over, but at a rate so slow in adulthood that a meaningful fraction of the heart muscle cells present at birth remain in place for decades afterward. Set against this backdrop, bone's constant, active remodeling looks less like the default state of the body and more like a specific biological strategy, chosen because a skeleton that can reshape itself in response to mechanical demand is more useful across an active lifetime than a skeleton frozen in whatever form it took at birth. The permanence of enamel serves a different purpose entirely, providing a hard, wear-resistant surface for a lifetime of chewing that does not need to adapt to changing loads the way a load-bearing bone does. Different tissues made different evolutionary trades, and the skeleton's trade favored constant renewal over fixed permanence. There is a practical consequence of enamel's permanence that shows up in forensic and archaeological science, and it doubles as a clean illustration of the same bomb pulse dating method described earlier. Because enamel forms during childhood and is never rebuilt, the carbon-14 signature locked inside a person's tooth enamel effectively freezes the atmospheric radiocarbon concentration present at the specific age when that tooth was mineralizing, providing forensic scientists with a reasonably precise estimate of a person's birth year from a single tooth sample, a technique that has been used to help identify unknown remains. No equivalent technique works nearly as well on bone, precisely because bone's continuous remodeling means its carbon-14 signature reflects an ongoing average of recent years rather than a fixed snapshot from any single point in the past. The same biological property that makes your skeleton adaptable during life makes it a poor clock for reading backward, while the same property that makes enamel useless for adapting to new mechanical demands makes it an unusually precise one. None of this is abstract trivia sitting apart from anything you can act on. The remodeling cycle described throughout this script is actively running inside you right now, responding, in real time, to how much mechanical loading your skeleton is receiving today, this week, this year. The practical thread running through all of it points toward the same conclusion from several different directions. Weight-bearing activity, walking, resistance training, any movement that compresses and flexes bone under real load, is not simply good general advice floating free of mechanism. It is the specific input the piezoelectric signaling system described earlier is built to detect, the trigger that tips the ongoing balance between osteoclast resorption and osteoblast formation toward net gain rather than net loss. This matters at every age, but it matters with particular weight after midlife, when the baseline balance between the two cell populations shifts, on its own, gradually toward more resorption and less formation even in someone who continues loading their skeleton exactly as before, which is part of why maintaining or increasing mechanical loading later in life carries outsized value compared to the same effort earlier on, when the underlying balance was doing more of the work by itself. There is also something worth sitting with beyond the practical advice. The version of your skeleton holding you upright at this exact moment did not exist, atom for atom, at any single earlier point in your life you could name. It is being actively maintained, continuously, by a construction and demolition crew running on electrical instructions generated by your own movement, and it will look, chemically, different again in a decade, made of different calcium, different phosphate, different collagen, still recognizably yours, still doing the same job, still shaped by the accumulated history of every step, every load, every stress it has ever been asked to bear. The X-ray in the drawer and the scan on the phone were never actually pictures of the same material. They were pictures of the same ongoing process, caught at two different points, still running, still listening for the next signal to arrive. Thank you so much for watching until the end. If you loved this story, check out the other videos on your screen now. I think you'll really enjoy them. And don't forget to subscribe if you haven't already. See you in the next story. The same property that makes enamel useless for adapting to new mechanical demands makes it an unusually precise one. None of this is abstract trivia sitting apart from anything you can act on. The remodeling cycle described throughout this script is actively running inside you right now, responding, in real time, to how much mechanical loading your skeleton is receiving today, this week, this year. The practical thread running through all of it points toward the same conclusion from several different directions. Weight-bearing activity, walking, resistance training, any movement that compresses and flexes bone under real load, is not simply good general advice floating free of mechanism. It is the specific input the piezoelectric signaling system described earlier is built to detect, the trigger that tips the ongoing balance between osteoclast resorption and osteoblast formation toward net gain rather than net loss. This matters at every age, but it matters with particular weight after midlife, when the baseline balance between the two cell populations shifts, on its own, gradually toward more resorption and less formation even in someone who continues loading their skeleton exactly as before, which is part of why maintaining or increasing mechanical loading later in life carries outsized value compared to the same effort earlier on, when the underlying balance was doing more of the work by itself. There is also something worth sitting with beyond the practical advice. The version of your skeleton holding you upright at this exact moment did not exist, atom for atom, at any single earlier point in your life you could name. It is being actively maintained, continuously, by a construction and demolition crew running on electrical instructions generated by your own movement, and it will look, chemically, different again in a decade, made of different calcium, different phosphate, different collagen, still recognizably yours, still doing the same job, still shaped by the accumulated history of every step, every load, every stress it has ever been asked to bear. The X-ray in the drawer and the scan on the phone were never actually pictures of the same material. They were pictures of the same ongoing process, caught at two different points, still running, still listening for the next signal to arrive. Thank you so much for watching until the end. If you loved this story, check out the other videos on your screen now. I think you'll really enjoy them. And don't forget to subscribe if you haven't already. See you in the next story.